So far, we have seen various approximation methods suitable for stationary problems or time-independent problems. Now, we will analyze one approximation method that is applicable in the case of time-dependent problems. And this method is nothing other than the perturbation theory, which we have already applied in the case of stationary problems. And this is the one and only approximation method that we will have to talk about as long as an approximate solution to time-dependent Schrodinger's equation is concerned. As we have already seen in time-independent perturbation theory, here also in time-dependent perturbation theory, the Hamiltonian of the system under our study, which now happens to be time-dependent Hamiltonian or mathematically a function of time besides the position coordinate, can be taken as a small correction or a small addition or a small disturbance or the so-called perturbation over the Hamiltonian of a known system. And the important thing is that the Hamiltonian of the known system is exclusively a mathematical function of position coordinate R only and is independent of time. So that the small correction in energy or the perturbation is simultaneously a mathematical function of position as well as time. This indicates that the Hamiltonian of the system under our consideration happens to have a time dependence arising exclusively from the perturbation term. So the time dependence of the Hamiltonian is exclusively coming from the time dependence of the perturbed part of Hamiltonian, or it is the perturbed part of Hamiltonian, say H prime, that happens to be the time dependent part of the Hamiltonian. And the applicability of perturbation theory, as you know, is limited to those problems whose Hamiltonian can be decomposed as the Hamiltonian, as the sum of the Hamiltonian of a known system and a small correction or the small perturbation in energy. Practically, there could be two different situations in which we can consider this kind of a time dependence of Hamiltonian, arising from the time dependence of the perturbed part of the Hamiltonian. One situation is that in addition to the unperturbed part of the Hamiltonian, the perturbed part of the Hamiltonian also found to be a position only dependent term. However, this happened for a fixed duration of time. So H prime, if you are looking into the explicit mathematical dependence of the function over time, it is found to be independent of time. But this perturbed part of Hamiltonian, which is constant in time, act for a definite interval of time or a definite duration of time, say from 0 to t. So that for this duration of time, this constant perturbation act, and this create a time dependent Hamiltonian because it lasts for a definite duration of time. A physical situation in which this kind of a time dependence of Hamiltonian can be viewed is in the case of scattering problem in quantum mechanics, or even if you consider the alpha particle scattering conducted by Rutherford, this can be viewed as a perturbation that is constant in time, happening or occurring for a fixed duration of time, evidently giving rise to a time dependent perturbed part of the Hamiltonian, hence a time dependent Hamiltonian. and ultimately creating or demanding, as long as we people are concerned, demanding an approximate solution for a time-dependent Schrödinger equation of the form IH cross dou psi by dou t equal to h of r comma t operating over the wave function psi of r comma t, where this psi of r comma t is written in bold letter, indicating that this is simultaneously position as well as time dependent wave function or wave vector. So once you are looking into the scattering problem, you already have a system that can be a nucleus, as in the case of the Rutherford scattering, having a definite charge for the nucleus, say Z into E, where E has its usual meaning, whereas Z indicate the atomic number as usual. Now, this system will have a Hamiltonian, say H0, rather than representing it as say H, because I am going to perturb this system very shortly. This is a mathematical function of position only, H0. As you know, H0 will have a representation H0 equal to sum of the kinetic energy and potential energy term, most often being written as a P square by 2 mu plus V. Now you have a projectile system which is assumed to be, say, coming from say infinity or from a very large distance, and this projectile is also supposed to be a charged particle as long as Rutherford scattering is concerned. And as this projectile reaches the very close vicinity of the nucleus, definitely this will be lasting for a definite interval of time. For that much duration, there occur an interaction between the projectile particle and the nucleus or the target as long as the scattering problem is concerned. This interaction definitely disturbs the system under our consideration, that now happens to be the system consisting of both the nucleus or the target material as well as the projectile. And once you look into such a system, the Hamiltonian of that system will be definitely a perturbation over the Hamiltonian of the nucleus or the target material as long as the scattering problem is concerned. And during this interaction, the Hamiltonian may be written as a H0 plus lambda H prime. Of course, this incoming particle or the projectile will also have a definite Hamiltonian that will be constant in time, which will be generally a position dependent parameter most often as long as particle scattering is concerned. So that this H prime happens to be a function or a mathematical function of position only. However, this lasts for a definite duration, so that for that much duration, the total Hamiltonian of the system under our choice, that is the system which will be undergoing this scattering involving both the nucleus or the target material as well as the projectile, will have a Hamiltonian that's equal to H0 plus lambda H prime. However, this lambda H prime will have a longevity or a life expectancy for a definite duration in which there occur an interaction between the target and projectile, so that this Hamiltonian of the scattering system happens to be a function of both position as well as time. So this is the first situation where we come across a time-dependent perturbing term which will be compelling the Hamiltonian of the system under our choice to be a time-dependent Hamiltonian. Another occasion where we will be encountering this kind of a time-dependent Hamiltonian that is viable to be applied, the perturbation theory, involve a mathematical function which is exclusively time dependent, which will be appearing in the format of a perturbation. This often occur in the case of physical situations that involve the interaction of radiation with matter. So I will tell you this second situation happens to be those situations where the perturbed part of the Hamiltonian exclusively do have a dependent over time in addition to its expected position dependence. As an example, consider the interaction of radiation with matter. The radiation, as you know, will be generally represented in the form of a sinusoidal plane progressive wave, or rather than a sinusoidal wave. It is usually represented by means of a transverse electromagnetic wave, and the energy carried by the transverse electromagnetic wave is represented in terms of the Poynting's vector. Whenever there occur interaction of this plane progressive transverse electromagnetic wave with an atom, then the Hamiltonian of the atom, which of course will be representing using the symbol H0 of R, will be disturbed in terms of this time dependent Poynting's vector that you can evaluate using the electric field as well as the magnetic field component of the electromagnetic radiation, definitely which will be a sinusoidal oscillation or a harmonic oscillation, or represented by means of a plane progressive wave which will have a harmonic dependence over time, so that the perturbed part of the Hamiltonian is exclusively a mathematical function in time, which will be making the system under our consideration. Here this happens to be that particular instantaneous system which involves the interaction of atom with the incoming radiation. And of course we will be interested in the effects of this interaction. What happens to the atom when it undergoes an interaction with the incoming radiation? As we already know from our knowledge on the interaction of radiation with matter, or from our knowledge on spectroscopy, there are two different possibilities when there occur interaction of electromagnetic radiation with matter. Either the material medium will be supplying energy to the incoming radiation, so that energy of the electrons occupying some of the higher states in the atom will be losing, and these electrons will be falling into some of its per meter lower energy states. This is associated with the emission of radiation by the material medium and is referred to as stimulated emission, which is reasonable for one of the prime invention in spectroscopy, that happens to be the laser. And in some other occasions, or most often, generally material medium will be absorbing energy from the incoming radiation. This energy that these electrons occupying some of the lower energy states of the atom absorbing from the incoming radiation will be used for their promotion from their lower energy states to higher energy state. And corresponding to this kind of a process, photon having energy equal to the energy difference between the final and initial states of the atom will be absorbed from the incoming radiation, and this process is referred to as the stimulated absorption. Rather than stimulated absorption, the word that will be generally used, or the phrase that is generally used, happens to be induced absorption. So generally we will be talking about this kind of different physical processes that can be treated as some consequences of this time dependence of Hamiltonian. So in brief, we can consider the time dependence of the perturbed part of Hamiltonian in two different scenarios. The first scenario is that we have a constant Hamiltonian which is constant in time, acting for a definite duration, making the overall Hamiltonian of the system under our consideration being time dependent. Example is scattering problem. Another occasion, our perturbation happens to be a time dependent perturbation. It can have a square or cube dependence of time, or can have a harmonic dependence of time. If it's a harmonic dependence of time, definitely the case that has some physical reality happens to be the interaction of radiation with matter. We have just seen the practical situations where we will be coming across some time dependent problems with the perturbed part of the Hamiltonian being time dependent. Now at this point I would like to tell you one more thing as an introductory remark. The immediate consequences of this kind of a time dependent perturbation happens to be the transition of the unperturbed system from some of its permitted stationary energy states to some other permitted stationary energy states, either following an excitation or following a de-excitation. Whatever may it be, the general consequence of this kind of a time-dependent perturbation, whether it is a scattering problem or it is some categories of phenomenon involving interaction of radiation with matter, the immediate consequence of time-dependent perturbation happens to be the transition of the unperturbed system from some of its, say, permitted energy states to some other energy states. Now with this introduction, we will look into the mathematical formulation of this perturbation theory. So we have a Hamiltonian that happens to have a time dependence, and this time dependence is expected exclusively through or via the perturbed part of the Hamiltonian. And we have to find an approximate solution for the Schrodinger's time-dependent equation satisfied by the system under our consideration, given by IH cross dou psi by dou t. Here I have made this psi, say bold, equal to h of r comma t operating over psi of r comma t. So in the mathematical point of view, our primary aim is to find an approximate solution for this differential equation, which is a time-dependent equation, and the operator involved in this equation also happens to be a time-dependent Hamiltonian. Now the knowledge that we do have the entire knowledge about the unperturbed system, which is assumed to have a Hamiltonian H0 of R, which is time independent and will be satisfying the Schrodinger's equation H0 of R operating over psi n0 of R comma t, where psi n0 is the stationary state, equal to En0 times psi n0. So H0 operating over psi n0. Here psi n0 happens to have both time as well as space dependence, with these time and space dependence being separable into homogeneous time dependent and space dependent terms of the form psi n0 of R e raised to minus I Ent divided by h cross, where Ent is nothing other than the energy eigenvalue of the nth quantum state. So H0 operating over psi n0 of R comma t equal to En0 times psi n0 of R comma t. So we already know all the orthonormal, let's say in the sense that orthogonal. Of course we will be normalizing them because they will be mapping the necessary Hilbert space for considering the problem. So right now itself I will tell you orthonormal eigenfunctions of this unperturbed Hamiltonians, say H0 of R, and this set is known to me. I will be marking this set, say finite set psi n0 n dimensional, or set ket n dimensional. With the psi n0 having this mathematical formulation psi n0 of r. So this is the space only dependent part of the wave function representing the stationary states, e raised to minus I en t divided by h cross, and this will be satisfying the Schrodinger's equation I h cross dou psi n0 by dou t equal to h0 psi n0. This will have a time independent format, h0 psi n0 equal to en0 psi n0. Because the time dependence is identical on both sides, you can omit it as it is in terms of e raised to minus I en t divided by h cross. Now, in the presence of h prime of r comma t, the state function under our choice is psi of r comma t. Now, the procedure or the mode of operation for time, whatever may it be, whether it is time dependent or time independent, perturbation theory is often common. The wave function in the presence of the perturbed part of the Hamiltonian, or the wave function of the system under our consideration, can be taken as a linear combination of the set of all eigengets of the unperturbed system. So that we will write psi of r comma t as equal to summation over n Cn of t psi n 0. Here psi n 0 do not have, say, a mathematical dependence of over time other than this non-mathematical formulation e raised to minus I en t divided by h cross. So it is safe to consider this expansion coefficient Cn of t also a time dependent parameter, as it is a scalar. In operations, we need not bother about the operator operating over this mathematical function. And this has one more significance. As I have already told you, our primary aim of considering perturbation theory is to identify that as a consequence of this kind of an interaction, which will be forcing the Hamiltonian of the system being time dependent in terms of the perturbed part of the Hamiltonian, whether there occur a transition of the system between its permitted stationary quantum states. And the probability amplitude of this transition will be represented by nothing other than this expansion coefficient, because the probability amplitude will be probability we will be evaluating in terms of the square of the wave function. As these psi n zeros are normalized wave functions, their scalar product with themselves will be equal to 1, so that our expression for probability happens to be simply equal to the square of these expansion coefficients, which are time dependent, or we have strong reasons to think that these parameters are time dependent, or these probability are time dependent, because we can expect, I will tell you, this is a warning, this is not necessary that it will be happening, but even then we can assume that if we make an interaction of radiation with matter for a prolonged interval of time, definitely there can be chance for higher extent of transition, or there is greater possibility of transition from the atom from one of its permitted stationary state to another stationary state. So it is in this point of view, I'll be taking this expansion coefficient as a time dependent. So this is equal to summation over n Cn of t psi n0 of r, the space only dependent term, into the homogeneous time only dependent term e raised to minus I en t divided by h cross of the wave function corresponding to, or the orthonormal eigengets of the unperturbed system. Now substitute this representation of the wave function representing the system under our consideration, that is the system involving this interaction, or that is the system having this Hamiltonian equal to the Hamiltonian of the unperturbed system plus the time dependent perturbed part of the Hamiltonian. So we substitute this in the expression that we have to solve, which is the time-dependent Schrodinger's equation satisfied by the system under our consideration, which is IH cross dou psi by dou t equal to H of r comma t operating over psi. So we substitute psi as summation over n Cn psi n0 e power minus I n t by H cross. That's equal to, we also substitute for H as H0 plus lambda H prime. For the time being, I have omitted lambda. I'll be retaining it whenever I am in need of it. For the time being, let me take lambda equal to 1. So this is H0 plus H prime operating over summation over n Cn psi n0 e power minus I en t divided by H cross. Now, here on the left side, I have to account for a differentiation in time, and these parameters that are to be differentiated include two time dependent terms. So definitely I'll have to account for the product rule of differentiation, first function into derivative of second plus second function into derivative of first. Here the first function happens to be Cn of t and the second function is e power minus I en t by H cross. Since n0 of r is constant in time, you can take n0 of r out of this differentiation. So we get IH cross, first function summation is retained, summation over n Cn into derivative of this one d by dt of n0 of r e raised to minus I en t by H cross. This time derivative has nothing to do with n0 of r, but I am interested in this term in this manner. Why it is so, that I'll tell you in the very next step. Plus IH cross summation over n is retained into derivative of first into the second function. D by dt of Cn of t into second function is the verb function, which is the product of the homogeneous time only and space only dependent parts. That's equal to, on the right side, H0 plus H prime is operating on this verb function H0 summation over n Cn psi n0 e power minus I en t by H cross plus H prime operating over the quantity in this bracket. Now you look at this term and this term on the right side, which I have now underlined. This is nothing other than the Schrodinger's equation obeyed by the unperturbed system. IH cross dou psi n0 by dou t equal to H0 psi n0. So you can cancel them in this equation. Or mathematically, I must tell you, let me subtract this equation from this one. Or this is also reasonable, since this quantity on this left side, which is underlined, is equal to this one. So this will be vanishing in the next step, and I obtain IH cross summation over n dCn by dt psi n0 e power minus I en t by H cross equal to summation over n Cn of t H prime psi n0 e power minus I en t divided by H cross. For IH cross summation over n dCn by dt, let me represent this in terms of the Dirac notation for the ket vector. Ket n equal to summation over n. See, in this ket representation, both the time dependent and space dependent parts are involved. Summation over n Cn of t H prime over operating over ket n. I am interested in evaluating or identifying the probability amplitude of transition of the system that is being perturbed from some of its stationary state to some other stationary state as a consequence of this perturbation. I have already made my point clear to you. This probability amplitude is somehow related to this expansion coefficient. So my primary aim is to find an equation for this expansion coefficient. This I would like to share you at this moment. So I am interested in obtaining an expression for Cn, or Cn of t, which I can evaluate from this differential equation for Cn, as this include d by dt of Cn. So mathematically I require a left side that is simply dCn by dt. So on the left side I already have a constant IH cross which I can easily take to the right side, but I'll have to omit this dependence over the ket n. For that I'll have to take the scalar product of this equation with, say, adjoint ket, say k. So to omit ket n, we'll have to take the scalar product of this one using another vector from this orthonormal set of eigenvectors. So take the scalar product by ket k. Scalar product IH cross is retained here. IH cross scalar product k summation over n dCn by dt ket n equal to scalar product k summation over n Cn h prime ket n. This dCn by dt has nothing to do with this vector, so this is a constant and is taken out. IH cross summation over n dCn by dt into scalar product kn equal to this. We will expand ket k in the adjoint ket space is psi k0 of r e raised to minus I e k t divided by h cross, where ek is the energy of the kth stationary state of the unperturbed system. Summation over n Cn h prime psi n0 e power minus I e n t divided by h cross. This is nothing other than, say, Kronecker kn, since it is the product of two vectors in the orthonormal space, or in the orthonormal set of vectors, say set psi k0's n dimension. So this is nothing other than Kronecker kn, and will have a value when k equal to n, and for all other values, say, or for all other vectors k different from n, this scalar product will be vanishing. So this summation has only one term being retained corresponding to n equal to k. If you take this summation, you will have to take dc1 by dt plus, dc1 by dt scalar product k1 plus dc2 by dt scalar product k2 plus dc3 by dt scalar product k3 plus etc. All these scalar products, say k1, k2, k3, etc. will be vanishing except scalar product kk. Corresponding to that, this differential term will be dck by dt. IH cross is retained. IH cross dck by dt equal to summation over n Cn is taken out of this operator domain, since it has nothing to do with these scalar products or this operator. So summation over n Cn is taken. Now e raised to minus I e k t by h cross could be taken out of this adjoint ket vector to make it, say, e raised to the complex conjugate of this quantity. This is the property possessed by scalar product. As you know, scalar product is linear with respect to the ket space for the post factor space and is antilinear with respect to the prefactor space or the adjoint ket space. So psi k0 is retained, h prime is written in the operator domain, psi n0 is retained in the ket space, and this exponent term that involved this, say, energy of the interacting quantum states are taken out. From the adjoint ket space, you will have to take the complex conjugate of this one. For that, we will have to replace I by means of minus I. So overall, this becomes e raised to plus I e k t by h cross, which is written here. And from the ket space, the parameter can be taken as it is, e power minus I e n t by h cross. This is reasonable because h prime will have an operation over this psi n0 of r, in the sense that we assume h prime has a time dependence which is not exclusive. That is in terms of the fact that the first case that we have already seen, the perturbed part of Hamiltonian is constant in time, however it acts for a definite duration. Even if this is not the situation, you can take this, provided this involves some operators that are some differential operators in time. Seldom they do. So let me take this flexibility that these terms can be taken out. E power I e k t by h cross e power minus I e n t divided by h cross, where e k and e n are two stationary states, or energy corresponding to two stationary states, say psi k 0 of r and psi n 0 of r permitted to the unperturbed system. So we get IH cross dCk by dt equal to summation over n Cn of t, scalar product k h prime n. This is nothing other than kth matrix element of this perturbed part of the Hamiltonian. In the very next step, we will be representing this as a h prime kn. Here we can combine the exponential term. E raised to it by h cross is common, so e raised to I into, here this is positive term, ek minus en into t divided by h cross. Now you look at this quantity ek minus en. Ek is the energy of kth quantum state of the unperturbed system, and en is the energy of the nth quantum state of the unperturbed system. Now I can look into this matter in a different scenario. En can be taken as the energy of that quantum state being occupied by the atom before this interaction that forces the Hamiltonian to be time dependent, and Ek is the energy of the final quantum state, say psi k 0, to which the atom undergo a promotion either following an excitation or a de-excitation. So I must tell you either a promotion or a de-promotion as a consequence of this interaction, which forces the Hamiltonian to be time dependent. So Ek minus En is the energy difference that occur as a consequence of this interaction or that happen as a consequence of this transition. Either Ek minus En can be positive or negative, provided Ek exceed En or Ek is less than En, corresponding to whether the transition is an excitation transition or a de-excitation transition respectively. So Ek minus En is the energy difference of the final and initial quantum states of the system. And we also know that E equal to h cross omega, or E equal to h into nu, or that's equal to h cross omega, as long as the photon produced during a de-excitation or being absorbed during an excitation is concerned. So that E divided by h cross has the dimensions of omega, the frequency or the angular frequency corresponding to the transition, as angular frequency corresponding to the state. So that Ek minus En divided by h cross, Ek minus En by h cross is the term involved in this equation. Ek minus En divided by h cross can be taken as the angular frequency corresponding to the transition from the nth quantum state to the kth quantum state, omega kn, or can be represented as say omega final initial, because k is a representative for the final quantum state occupied by the system following this interaction, and n is a representative of the initial, generally the initial quantum state occupied by the atom, or say the system which is unperturbed system before the interaction. So we simplify it as a IH cross dCk by dt equal to summation over n Cn h prime kn, the matrix element of transition, e raised to I omega kn into t. So this is the expression this is the differential equation for the expansion coefficient corresponding to the transition. I have already told you Ket K is the representation of the final quantum state. Then Ck corresponds the probability amplitude of transition from psi n0 to psi k0. Under such a situation, you can represent the wave function representing the interacting system, or the system involving the interaction, or the system involving the perturbation as a linear combination of this psi k0, or the possible psi k0s, or all the possible psi k0s. But if you are looking at a single atom, it can have a single initial energy state, and it can have only a single final energy state. So once you are looking into the specific case of a single atom, then psi n0 and psi k0 has one and only one option, as long as the initial quantum state and final quantum state are concerned. There is only one initial quantum state, say Ket n, and there is only one final quantum state, say Ket k. And we are interested in analyzing the transition from this initial quantum state to this final quantum state. If you have only one choice for the initial quantum state and final quantum state, then definitely the expansion coefficient corresponds the probability amplitude for a transition from this state to this state, because you evaluate the probability as the square of this wave function. Once you take the square of this wave function, Ket k with having a scalar product with itself will be making it to be, say, equal to 1, and the additional term Ck will be squared once you take this square, or say take this probability evaluation. So the probability will be proportional to Ck square, so that the probability amplitude will be represented by Ck. It is that parameter which I am interested. So specifically, I have got now a differential equation for Ck, and of course I'll have some interest of solving this. Before that, we will have to consider the order of perturbation as long as the time-dependent perturbation theory is concerned. In the earlier case of time-independent perturbation, these are in terms of the order of perturbation. Here, however, this is slightly different, because we assume that the time dependence will be represented in terms of this single parameter, or say will be delegated by this single parameter, say Ck of t, the expansion coefficient. As usual, to evaluate the order of perturbation, we represent h prime in terms of the perturbation parameter, say lambda. So h prime is lambda times h prime. Once you put this in the equation for Cn of t, it can have different orders of perturbation in terms of the different powers of lambda. The unperturbed system may be represented to have Cn0 of t lambda power 0. Since it is not perturbed, there is no perturbation coefficient. So that Cn of t in the presence of the perturbation can be expanded in terms of different powers of the perturbation parameter, Cn0 of t plus lambda Cn1 of t plus lambda square Cn2 of t plus etc. Now we substitute this value of Cn in this differential equation for Cn. Actually it is for Ck, so when I come across k, I will be replacing n by means of k. So this becomes IH cross d by dt of Ck is Ck0 plus lambda Ck1 of t plus lambda square Ck2 of t plus etc. That's equal to, on the right side we have summation over n Cn of t, which is Cn0 of t plus lambda Cn1 of t plus lambda square Cn2 of t plus etc. into h prime kn is replaced by lambda h prime kn e raised to I omega kn into t. Now compare the different coefficients of the different powers of lambda on both sides. First of all, lambda power 0. On the left side, you have only one term containing lambda power 0, which is IH cross dck0 by dt. That's equal to, on the right side, all terms will have at least lambda, because you already have lambda outside of this bracket. So lambda power 0 term is not there on the right side, so the coefficient of lambda power 0 on the right side is 0. This indicates this has only one meaning. As you know, ck0 is a constant. That is the unperturbed system for zeroth order perturbation. So the first order term indicates that ck0 is constant in time. Now compare the coefficient of lambda term on both sides. On the left side we have IH cross dck1 by dt equal to, on the right side, summation over n cn0 times h prime kn e power I omega kn into t will be involved in lambda power 1. So summation over n cn0 h prime kn e power I omega kn into t. For the second order term, we compare the coefficient of lambda power 2 on both sides. We get it IH cross dck2 by dt equal to summation over n cn1 h prime kn e power I omega kn into t. Now you look at the first order perturbation term, because this will be the one and only significant term as long as our limit of accuracy is concerned. As we know that the perturbation parameter lambda is an extremely small quantity. So the significance of higher order terms of lambda in this expression will be extremely smaller, because lambda itself is a very small parameter. The square and cube terms of lambda will be then negligibly smaller. So within the limit of the accuracy in which we are interested, we will be generally contented with the first order term or correction up to the first order term. So we look at this term IH cross dck1 of t by dt equal to, or say I have divided IH cross to the right side, dck1 by dt equal to 1 by IH cross summation over n cn0 h prime kn e power I omega kn into t. Now from this we have seen that the zeroth order term is constant. Then so do Cn0, which is the zeroth order term as long as the initial quantum state is concerned. So Cn0 is constant in time or is independent of time. And this is the expansion coefficient or the probability for finding the system in the initial quantum state. Definitely the system might be occupying an initial quantum state. It is already there and the probability will be 1 then. This permits us to have a freedom of choosing Cn0 equal to 1, because the system needed to be in a definite quantum state before this interaction. As a consequence of this interaction, this undergo a transition to eigengates, say psi k0, a permitted another quantum state to which there occur transition. That is the final quantum state. So now this is a one-to-one relationship between an initial quantum state psi n0 and a final quantum state psi k0. And the transition probability or the probability of transition from an initial quantum state psi n0 to a final quantum state psi k0 is represented by the expansion coefficient Ck that we have to evaluate. Since the system is occupying an initial quantum state psi n0, the expansion coefficient corresponding to that particular quantum state Cn0 will be definitely equal to 1. So that the probability is 1 square, which is 1 itself, that indicates that the system already occupies this quantum state. This is true, or this is expected, since the system needed to be in a particular quantum state before this interaction takes place. As a consequence of this interaction, either the system will be occupying the same quantum state, that indicates that Ck is equal to Cn for that particular special case, or there undergo a transition, either an excitation or a de-excitation from this initial quantum state. Whether whatever may it be, whether it is an excitation or de-excitation, we represent it in terms of the parameter, say Ck, representing the probability amplitude for a transition to a final quantum state. So Ck1 of t equal to, we have dCk by dt on the left side. Taking the integral of this equation, we obtain Ck1 of t is equal to 1 by IH cross integral summation over n Cn0 h prime kn of r comma t e power I omega kn into t dt. I have told you that during the derivation h prime kn is constant in time. Even if it is not constant, I can put, say, time dependence here, and this term is retained within this integration. So now let's consider the argument that I have just mentioned. Initially the system needed to occupy a particular quantum state that is being represented by the, say, initial quantum state psi n0. Then the probability for finding the system in that particular quantum state is unity, and the probability amplitude corresponding to this particular quantum state is Cn0. For this probability to be unity, Cn0 needed to be unity. And Ck0, when t equal to 0, Ck0 is 0, because initially the system is occupying. If you are considering an atom, the system under our consideration is then happens to be this atomic electron. Atomic electron will be occupying an initial quantum state, say psi n0. The probability amplitude for this occupancy needed to be, of course, will be representing this in terms of, say, Cn psi n0, since psi n0 is a normalized eigenvector. So the probability for this occupancy needed to be 1. That means Cn is equal to 1. Since the atom is occupying initially the quantum state psi n0, it is not occupying the quantum state psi k0. Then the probability amplitude corresponding to this psi k0 is 0 when t equal to 0, that is before applying the perturbation. Now the perturbation acts for a definite duration, say t, so that there occur, or we have strong reasons to believe that there occur transition. If transition do not occur, that means Ck equal to Cn. If transition occur, that means Ck needed to be evaluated. So Ck1 of t equal to 1 by IH cross. This integration will be then from 0 to t. H prime kn of r comma t e power I omega kn t prime dt prime. So the probability amplitude of transition from an initial quantum state ket n to a final quantum state ket k is represented by this probability amplitude Ck1 of t, that's equal to 1 by IH cross integral matrix element of transition between final initial e power I omega kn t prime dt prime. Then the probability for transition is square of the probability amplitude, as you know, that's equal to Ck1 of t whole square. Now this is the expression for the probability amplitude of transition under time dependent perturbation. Now to proceed further, we require some cases of h prime kn. As per the demand of our syllabus, we will consider h prime corresponding to scattering problem, where h prime will do not have explicit dependence on time. It is a mathematical function of position only. However, it lasts for a definite duration. It is in that manner there occur time dependence. Such a perturbation is constant perturbation, and another occasion where we come across this kind of system happens to be the interaction of radiation with matter, where the perturbation happens to be a harmonic perturbation. Now we will look into the specific cases of constant perturbation and harmonic perturbation that we will see in the next video.